Okay, welcome to today's webinar, Putting the M into STEM, hosted by Texas Instruments Australia. My name is Peter Fox and I'll be your host and a panellist for today's event, and I'll be joined or accompanied by Mr. Jody Carruthers, who comes from Safety Bay High School all the way over in Western Australia. Let's see if we can get Jody on the line. Are you there, Jody?
Yes, I am. Can you hear me?
I can certainly hear you. Hopefully our participants can hear you as well. So, we're going to jump across to a video to introduce this topic for this evening's webinar. If you're wondering where the actual inspiration came from for the webinar, it's kind of come from a mixture of spaces, and that is teachers and schools wondering how they're going to incorporate STEM. It seems to be fairly well pushed from all sorts of areas, but none of us really trained as STEM teachers. So that poses a few problems. Who ends up teaching it? Then, of course, there's the finding a good context, and that's where our rover and autonomous vehicles fit in. So most people are familiar with Texas Instruments through our calculators and obviously with some of our data logging equipment that we have, but one of the largest parts of our company is actually semiconductors, and we work, or our semiconductor team, work in the automotive industry as well. So the video that you're seeing on the screen is some of the, I guess, cool chips that they have available for the automotive industry that include helping the idea of an autonomous vehicle, that is a vehicle that will drive itself. Now you can see that poor lady has just put the cup on the roof of her car. She's getting into the car. She's about to drive off. That would be a problem because we know what's going to happen to the cup of coffee that is in that cup. So she'll start up the car, set her destination, and oh, look at that. There's a warning that there's an object on the roof. So we can put sensors all over the car, whether it be to tell us about another vehicle coming towards us, or just as simple as reminding us that we left our keys or bag or something on the roof of the car. In-car entertainment systems, I guess if you don't have to manage the steering wheel, there's all sorts of things you can do. Still got a head-up display, which is interesting if I'm having the vehicle drive for itself. There's all sorts of wonderful videos you can watch on driverless cars that give you an idea on the sorts of problems that they will create and also some of the problems that they will solve. So a couple more seconds on this video. In this particular case, there's some weather warnings coming up, and all of this is just being done by this intelligent car. What you're seeing on the screen now poses huge problems. It doesn't seem like it, but rain, so you can't just use one sensor. So Texas Instruments create a fusion of sensors, which is a mixture of LiDAR, radar, and a few other sources and video to identify objects. So you can see there that it's identifying a human as they're walking across the road, and that can be quite challenging, picking up a human compared to some other things. And here we have one of the themes for tonight's or today's webinar, and that is a vehicle that will actually park itself. So the occupant gets out of the car, and then some people have already got these vehicles, so it's not, I guess, new to them anymore. They're just used to it, and the vehicle parks itself. So later in this webinar, we'll actually look at the mathematics behind that. We use TI-Nspire or TI-84 to simulate the event, and then we get Rover to actually do the parking. That is, the rover will follow the equations set up by the students to park, including parking in a spot where the students don't know the distance. Rover has sensors on it and will measure the distance, but the students have to have set up the equations so that it will park in any size spot as determined by the sensors on Rover. So let's have a look at Rover. We'll jump out of that one, and I'll close that one off, and we'll come into this one. So there's an array of sensors that we can see on the screen at the moment where it's picking up vehicles in front of us. Now, Rover has a sensor on the front of it, and that's used to detect objects in the distance. It's also got another sensor underneath it, which you can use as a lane guidance system. Now, why is it called TI-Innovator Rover? Well, that's because it's Rover plus the TI-Innovator. The Innovator is a board that our semiconductor team have helped put together, where students can program the microprocessor chips on board that device. It sounds complicated, it's not. We've actually made it really easy. The idea of using just basic programming to do it has made it far more accessible for lots of students. Now, if you're getting Rover out of the box for the first time, before you insert the Innovator into Rover, you'll need to make sure you have the latest version of Sketch. Sketch is like the operating system. Most people are familiar with updating the operating system on their calculator. Well, Innovator has an operating system on it as well. We've made it really easy. I know I've included a link, so if I hover over that image now, you'll see that there's a link, and you'll get this PowerPoint so you can follow it along. And that link will take you to our website where you can download the software, and it's as simple as plug Innovator into your computer, run the software. The software will check to see whether the Innovator is up to date, and if it is, it leaves it alone. If it's not, it'll prompt you and say, would you like me to update it? And just proceed, and within a couple of seconds, your Innovator will be ready to go. So that's step one. Step two, in the actual box that Rover comes in, you'll see there's a ribbon cable, and the most important part here is that the wire with the little red line is connected up to the power, and you'll see on the actual Innovator board, the breadboard connection there, there's a section on the right for power, and it's important that we actually align that one. You'll also notice, because when you put Innovator into the Rover, you'd have to twist the cable in an unusual way if you put it in the wrong way, so there shouldn't be too many problems, but that's just in case. Now, step three, you can be ready to slide Innovator into the actual Rover body itself and then connect the little ribbon cable. That only connects in one way. There's a little lug on the pin so that you can only plug it into the device in one way. And you're more than halfway through now. In fact, you could say you're 60% of the way through. In step four, the I2C cable, which is a small cable that plugs into the other end of Rover. You don't need to know what it does, except that it allows us to do lots of things at once with Rover. And then it just extends along the side of Rover and then plugs in the top. I find that I can sneak that cable underneath the ribbon cable just to make sure that it's tucked in neatly and out of the way. And you've got one step to go, and Rover is up and running, ready to go. You may have to charge Rover when you first get it. I didn't mention that. So you buckle Rover in, and if it's a TI-84, as you can see on the screen there now, then you just rotate those little clips for the CE, and if it's a TI-Nspire, you just turn them the other way. Then you connect your calculator cable into the TI-Innovator hub, and Rover's ready to go. You probably need to switch it on as well. That's going to help. Rover's going to beep at you, or your Innovator will beep at you if you don't switch it on. So you can run this from the TI-84. The commands are located in the program menu, and that's why you need to make sure you've got the latest OS on your calculator as well. So when you're in the middle of programming and you press the program button, you'll see that there's an extra menu there now. So we've got control, input, output, color, execute, but also hub. And all those Rover commands and Innovator commands are sitting in there. You'll see option number 7 is for Rover, and it'll bring up a whole list of commands applicable to Rover. It's in exactly the same position, exactly the same number of prompts if you're using TI-Nspire. So you go into Hub when you're programming, and you can see option number 7 is for Rover. So let's have a look at how difficult Rover is to program. Let's create a program that would just simply make Rover drive forward. Nothing else, just plow on forward. So we'd go into a program, and the first thing we have to do is tell Rover, or tell the calculator rather, that Rover is actually attached. So whenever you're writing a program for Rover, that's the first thing that has to go, first line. And once we've done that, then we can use a command such as send rover forward. This is one of Rover's driving commands, and that's it. That's your entire program. And for that, Rover will just simply drive forward. We haven't told it how far, when to stop, what to look out for. So at this particular stage, he's basically driving forward blind, no guidance whatsoever. We can also suggest a distance. Now these are rover distances, so that would be 20 centimetres. Jody might talk to you a little bit more about that later on, because he's got a program where Rover does some drawing. You'll see that Rover has a little pen holder at the start or at the front, and therefore you can scale the drawing down by scaling the grid down, because Rover's pretty clever. He can follow X and Y coordinates or create them. All right, so what else can Rover do? Rover can turn right. Now, just like the forward command, we can put a number in there if we wanted to. So, by default, Rover will turn right, which would be 90 degrees. Or Rover could turn left. Or you can put an angle in there. Before I go putting any angles in there, let's see what else we could do with just those two simple commands of driving forward and turning right. So we're focusing on our two commands. Everything else is just, I'm going to say, superfluous, because it's just the setup stuff. So if we pull those commands apart and make it Rover do them 4 times, you could copy and paste them. But let's say Rover was to do those two commands 4 times. What does that look like? Oh, let's have a look. First part of our program says, well, you need to connect Rover, so that's so that your calculator knows that Rover is attached. And then we'll focus on those two commands that Rover is going to complete 4 times. If you've not seen a for loop before, this might help you understand it. So for I equals 1 to 4, or as I like to say, for I is 1 to 4, because it will drive the English teachers mad, because that E in STEM is not English, it's engineering. So when I equals 1, Rover's driving forward and then turns right. Then when I equals 2, Rover drives forward and turns right. When I is 3, I love that, I is 3, and then I is 4. And Rover's done. So Rover draws a square, which means if we're thinking about mathematics and what we would do with that, the next logical one might be, how could Rover draw a polygon of any number of sides? So if we prompt the user, that's what that request statement does, it asks the user a question, number of sides, at which we would put in that value that the user enters into a variable called n. And then our loop will go around n times. So if the user put in a 3 and said for I equals 1 to 3, Rover would drive forward. And if we wanted to draw a triangle, and this is where the mathematics comes in, our M in STEM, it's interesting because most students would probably think 60 degrees. In fact, some teachers will think 60 degrees. But when you actually do this, and I did this with a colleague of mine up in Queensland, and we had one of her children who was in primary school doing this with us. And it was interesting because what this person's daughter did was actually stood there and pretended to draw a triangle herself. So rather than having Rover just jump into it and make a mistake, she stood there and drew the triangle herself and then started to work out what number of degrees do I need to turn for each angle. And we're talking about the exterior angles. And the only real prompt that we had to give her was, think about where you started, think about where you finished, that is, you've turned around, let's say, 360 degrees, and you did 3 turns, meaning 120 degrees. And then we can lean towards the general solution, which would be 360 divided by n, which is a really simple way to do it. And that can be evaluated in that send command that you see where it says right turn. We can actually put in an evaluate command that says write and evaluate 360 divided by n. Rover's now drawing a polygon with n sides. So there's a nice start-off lesson to have TI-Innovator Rover drawing a polygon and doing some basic maths. So I work in the TI office, but Jody Carruthers over there in Western Australia, he is a classroom teacher. I was originally, but Jody is still in the classroom, and he has a whole bunch of Rovers, and he's been working with his students over there in Western Australia doing some work with Rover. So I'm going to handball across to Jody, and he will show you some of the things that he's been doing with his students. And just while I'm doing that, if you have any questions, please send them in through the chat window and send them to all panelists. So you there, Jody? Yes, I can see your screen coming through already. Good stuff.
Bring the M into STEM. Good afternoon, good evening. It's only 4:20 here. You're very late now. You've got daylight savings. I hope that's serving you well. We have plenty of sunlight over here.
Yeah, the curtains don't fade as much now.
Good. And the cows have confusion with the milking times for you guys, so our cows know what they're doing at the moment, which is really good. Just going on from Pete's triangle, that's what most of my students ended up with the very first time they decided to draw a triangle, turning 60 degrees each time.
Nice, nice. Did you tell them that they'd half finished a hexagon?
I didn't get that far. I just said, do you think that's a triangle? And they went, no. I said, that's good, because it's a wonderful place. Everyone can get things wrong, and that's the beauty of this. They can get things wrong, they can start again, make some corrections, and go ahead and do it again. So I'm going to take you through the forward command, but I'm actually going to go to the software and just show you how simple it is to program. I've had the rover. I had one rover, luckily, about 12 months ago, and I started playing around with my Year 7 students. I've been lucky enough to pick up another 4, so we've got 5 with the class. We probably need a few more, but we work in groups, and we have a chance to have conversations about what's going to happen, what we think is going to happen. And so it's simple enough that the students with no programming background have been able to pick it up and run with it. So they find a new document, they go to the program editor, and they create a new program. And often I call it smooth, because that's a nice simple thing. And we go, okay. And so I talk about, as Peter did, about connecting it. So menu, we've got the hub, and we want to connect the rover, step by step. We've connected it, now we can make it do something. Menu. And
just while Jody's doing that, you'll notice Jody's using the menus. So it's designed so that when students are using the handheld, you see they don't have to do much in the way of typing. And it's all written, so that's fairly straightforward, isn't it, Jody, in terms of forward, back, left, right, stop, resume. And most of them are fairly logical sort of statements, aren't they?
That's correct. And for these guys, menu 871 gets them just about everyone. Once they're connected, and they're going, oh, menu 871. And then they choose which drive command they're going to do, because they like driving to start with. And for the Year 7s, that's a really good starting point. As Peter was saying, these wonderful units are in lots of 10 centimetres. And so the kids thought they were centimetres initially. So the first kid did something 25 centimetres, and 2.5 metres, it stopped. So they had to have some conversations about what was happening, about the units we're using, why we're using that. I've actually got a large white piece of Corpholite that we've actually got some lines on and created our own grid, so we know how far these distances are. And from there, we can go menu, check syntax store, so Control R or Control B. Control B will check the syntax and store it, and Control R will actually run our program. So what does it look like when it moves? Well, here it is. This is moving 3. It's as simple as type it in, Control R, press enter, and there we have it. It moves forward 30 centimetres. Absolutely thrilling. The kids loved it. Well, not quite. The next one we looked at was the turn command. They can go left, they can go right, and looking at the angles. Let's turn right 180 degrees. And it was as simple as that, turning right 180 degrees, spins it round. What's the first thing that most of the boys in the class chose to do? 360s. You can't do more than 360 because if you go 380, the rover knows and just does the 20 and gets it to the final place. So that's something. So they wouldn't do 360 after 360. They'd have to do that command, then do it again, and then do it again, and then do it again. And again, really simple process. Menu 871 gives you access to all the drive commands: forwards, backwards, left, right, stop, resume, stay, 2XY, which I'll talk about a bit later, 2 polar, and 2 angle. So you can actually have it doing some quite complex things. Even with your specialist kids, you can get graph polar equations. And that can be fun for everyone to be able to access and actually be able to see whether their equation and the things they've come up with are correct. So, the right, 360, we'll do the full 360, or the 180 as I did before, we'll turn round. So we get the rover moving, and the rover moving is great. It's that physical programming. The kids get to see what's happening. I'm lucky enough at my school to have a cheer dance program. So we have internationally reputation. Our kids travel all around the world to cheer dance competitions. And some of these girls lack a bit of confidence in maths. We don't have any boys in the program. But we talk about algorithmic thinking and the fact that they are doing plans and routines all the time. So we got one rover, they got it moving. They said, can we combine them? So here's one, here's me and my son going through and showing an example of one of the simple programs they came up with. They wanted to make a rover dance. This is a slow motion version. Executing the program all at the same time.
Now, I was thinking about that one, Jody. What we haven't mentioned here is the fact that you can plug sensors into Rover, and I was thinking about that is that you could plug an audio sensor in, a microphone, or a light sensor, and you can actually cue them to start by having a loud clap or a flash of light, and then they would all kick off at the same time, which would be kind of cool.
Yeah, and that one seemed to crash. It didn't work as well. So we'll go back to one of the...
No, that's okay, because one of the teachers we know, Jody, is doing simultaneous... Oh, that's nice. It's kind of like line dancing, but not. He's doing simultaneous equations with them, which is kind of cool. Getting them to crash on purpose.
Yeah. So they come through and they hit. And instead of doing STEM, you're doing STEAM. You can start coordinating some of these things together, start getting a dance routine happening. And so that's our next thing, to get the kids to look at the timing, to look at the motion, and put the two things together. So
yes, because you can control the speed as well, can't you? So you can control the speed that Rover's moving along and for how long, which is kind of cool.
That's right. And if there's one person running it, and I did a few activities, you can start it and have a wait command there. So I can start one, start the second, start the next one, start the next one, start the next one, and they can all take off at the same time. If there's one person controlling it. So they can start to have thinking about what needs to happen. The things happen at the same time at the end of what times you need to start. So I wonder if you can even think about some project network stuff like that. What can move where and when to actually have everything finished at the same time. So let's go back to here. Now, other things. The rover has some wonderful sensors. One of the sensors it has is the ranger, the little eyes at the front, ultrasonic ranger, so you can determine distances. So I'll show you how the program works, then I'll show you the program. In this video, you'll see the TI rover trying to find something. Technical name, find stuff. Spins round. Taking readings every 30 degrees.
It's interesting because what it's actually doing is very similar to what LiDAR does. LiDAR is using a laser, and it basically rotates and measures the reflected beam. So it's doing it many, many times per second, and therefore plotting the location of points effectively on a grid of the points or objects that it's found by just spinning a radar around. So this is just a slightly slower way of doing that, but it's still the same idea, isn't it?
That's right, and it's conceptually getting the kids to think about what's going to happen. And my Year 7s aren't up to there. After a couple of years playing with it, I think they'll be closer to it. But we could basically create a program, distances, angles, and it goes around. It spins around and finds those things and puts all that information, got a handheld view, probably easier, puts it all into it. Puts it all into a set. So if I actually want to go through a list, I've got distances and angles, sets of values, and then it evaluates it. It sorts them. So by sorting them, we get them in order. Then it chooses the first value, which should be the shortest, finds the appropriate angle to go with it, spins at angle, goes that distance, and finds the object. The other one, the sensor that we have, just a second, I've got it.
Now, if it was a really clever rover, Jody, you know it would actually retrieve it, wouldn't it?
Well, that could be the next step. You've got a lot of other engines or motors you can connect, and you can actually have it do things like that. And that's a way of the future. The other thing we can do, and we'll have a look, is the wonderful thing, drawing a picture. Late last year, we were lucky enough to add a command, the 2XY. With the Year 7s, Australian curriculum covers drawing Cartesian coordinates. And as most people with the students have done, we do Cartesian coordinate pictures. And we give them the points, and they draw the points, and then we give them pictures, and they get to draw their picture, and we see what it looks like, and get their friend to check it. Well, rather than that, once the kid's drawn their picture, drawn the Cartesian points to go with it, I can get them to put them in this table of value. As with everything with the TI-Nspire, when we get to our columns in our list and spreadsheets, we label them. I call mine X val and Y val. I could call them X and Y, but every time I used them, they'd ask me whether it was a column reference or a variable reference, so I'd rather make it really distinct to start with. And then I graph it. Menu, graph and entry. And I do that as a scatter plot, point by point, and then I join the points. And as you can see, here's my lovely pi symbol. I had one of my Year 7 students go through, it's coming out to Pi Day, oh, can you draw me pi on here? And the only one parameter I gave them is I wanted pi to start at the origin. Rover, with the pen in there, doesn't have a pen up and down function built in, but some people have built it with other motors and stuff. So it likes having the pen down straight away. So as long as the diagram starts at the origin, we're fine. So from there, we've done that. Then I wrote a simple program, and it's probably got 2 or 3 lines you don't necessarily need to do. It connects to the rover. This one here you might be unfamiliar with. This is setting the grid. So the default grid is every unit with rover is 10 centimetres. So a 10 by 10 grid would be a metre by a metre. And that's fine for a lot of things. For what I wanted to do, I wanted to draw on a piece of paper. I didn't have a metre by metre piece of paper. So I went for 0.05, so a 20th of it, to make it smaller. And again, dimension values, it's looked at my X value row, counted how many values we've got, and moved us from point to point to point to point to point to get to the end. So
I'm guessing if rover goes over 0.05, the lines are not straight anymore. Is that how that works, Jody? If you pardon that pun?
I'd have to have a look. I didn't actually put it on my piece of paper, I'll be completely brutally honest.
No,
so,
I'm just having a pun on the 0.05 limit, that was all, that Rover wouldn't be able to draw a straight line if he goes over 0.05.
We can really walk the walk then. We're interested to see how it goes. And simply, we got it going. We've got one there we've previously done. If you're doing the drawing with the Rover, make sure you tape your paper down, because it will grab and slip and not quite get correctly.
And always best not to use a permanent marker either, just in case Rover drives off the edge of that paper.
Well, I do have some photos I have posted on Twitter when one of my curves, my polar curves, didn't quite match up with the piece of paper I was using, and did go over our wooden floorboards. But my wife wasn't home, which is good. I managed to get that before me. And
if teachers are looking for other ideas on other symbols, we have an activity on the website which has students doing a graph or a scatter plot around their hand. So they trace their hand, and the mathematics behind it is obviously plotting all the points and writing down the coordinates of those points, and doing exactly the same as what Jodie's got on there, is to literally just get it to go from point to point to point. And you saw Jodie's program. It was really about, what, 4 or 5 lines required to do it, and that was it.
Yeah, and the other ones we had a look at was doing some 4-leaf clovers for St. Patrick's Day as well. So they're the ones on the program. Even just drawing pi, I've altered it. We've plotted those points out, and from there, before we hit the Rover with it, we'll translate it across so one of those points is starting at the origin to follow through. So the Rover can go through and draw me a 4-leaf clover, which would make me very, very lucky. And there's a copy of what we're doing. Now, the other thing I've been doing recently, and ran at a recent STEM conference we had in Western Australia, was using the Rover to look at graphs and motion. So, graph challenge maths. So using the Rover on a time position map.
I like that.
Oh, you had your own session on, you missed this one. So, the challenge was to get the Rover to draw, or to move in a way which matched that curve. Now, for those people who want to do, this one here is really good, one of my favourite videos. And I'll just find out when
Is that the one there?
Yeah,
that's pretty funny, Jody.
So this one here will go. And that has the graph moving from away, closer, stopping, moving back. So then we go have a look at our graphs. It matches up with this one. Moves from away, closer, stop, comes in. So having a look at that. So then we can go to some of the other ones. Yep.
Let me guess, that's the horizontal line?
That's only one of the horizontal lines. Which one is it?
I'm guessing it's the one that's furthest from the x-axis because the displacement is bigger.
Well, it depends where you do the displacement from. That's actually closer.
That's
this
very
one
true.
Here because the head of it was there. So we look for the other one. We can match that one. We can go back. And I think it's this one. Yeah, this is further away. So I really need to get out more because I've got all these videos actually on my YouTube channel. But
pretty funny,
apart from doing above, I did the same sort of thing from behind.
Oh dear.
So this is, well, a chance to have a look at, for the kids to see. Whoa! And this is the first one we looked at, where it goes, waits, and then comes closer. Whoa! It does some sensors at the back as well. So that challenge for the kids to actually match the videos with the graphs. In this case, it was the teachers. But the next step was come up with some graphs and create the motion using Rover so they can actually see what's happening. And that's good for your physics kids doing rectilinear motion, but it's also good for your year 7s and 8s doing travel graphs.
In fact, the extension of that would be having different slope on the graph too, wouldn't it? And getting the kids to look up the speed commands and then associating that speed with the actual graph itself.
That's right, and you can get to more and more levels of detail. But just as a generic concept, to be able to see what was happening. And here, there are differences, so they realise this speed out here, stationary, then comes back faster. So it's travelling faster here. When it's horizontal, it's really, really boring. It just sits there. And so challenge the participants to think about graphs, think about what they mean. So when we have someone travelling from home, stops at their friend's place, they travel towards school, and it's distance from school is the position, they can actually have a feel for what's happening. So Peter, that's what I've got for now. Do you want to go on with some more of your stuff?
Yep, I'll drag the ball back to myself.
But it's really engaging for the year 7s. And we actually ran the Hidden World of Maths at SciTech, which is like Questacon in Canberra. SciTech's our equivalent in Perth with the general public. So my son and I ran a whole lot of stuff with the rover, down on the ground, having the kids make it move, spin, actually having the program talking about distances and time and getting close to objects, the nearest to something, having them estimate. I'm not going to let you measure what you estimate that wall's going to be. Let's make the rover travel that far. If you get it right, it stops just in time. If you get it wrong, it hits it. If you get it wrong, it's too far away. So that power of estimation, because a lot of the kids hate estimating.
Yeah, well, that's why they like to know the exact answer, don't they? And we sort of say, well, that's not how most of the things around us work. So Jody was using a lot of different commands there. You saw that he had one where he was using the motion sensor at the front. There's a light sensor which also detects different colours, so you can have the usual line tracking, or as I'm going to refer to it as lane guidance, because that's effectively how a car is working, looking at indicators on the road. This is on the TI Australia website. I've just gone into products and looked up for TI-Innovator, and you'll see that the Rover is in amongst those. That's because the Rover needs the Innovator. That's Rover's brain there. There's a little video to give you some ideas, and there's also a section called Resources. Now, this is where you'll want to go when you're looking for ideas in terms of the commands. So there's an e-guide. You can download a complete PDF. My preference, however, is for this e-guide because it allows you to search for things. And the search tool is very powerful. You can go through the page of contents. I'm not that kind of person. I just want it, and I want to know the answer now. So if I did, say, for example, Ranger, and ask it to search, then I'm going to have a look through the list of items that it returns in that search. So, for example, RV, short for Rover, Rover Ranger, it's a bit of a mouthful. If I click on that, it tells me, connects the Rover vehicle to the Innovator Hub, this establishes connection, and then it says read RV Ranger, and then get R. And it tells you what happens. If there is no obstacle, it will detect a range of 10 metres. And that's the entire command, read Rover Ranger. And if you're wondering, now, where could I find that? In other words, if I was in the software or in the program and I'm doing something, let me just start up a new document. And we'll do Program, New, I'll call it Stuff, to match what Jody was doing. And, of course, obviously the first thing, if I'm working with Ranger, is I need to connect it. And then if I want to read Rover's Ranger, that's a mouthful, isn't it? You can see there's an option for read RV sensors. And there it is, the first one. You can see there's the colour input ones for the base of the Rover as well. And then the next thing it said to was do a get. And I'm going to put D there for distance. and then I could display it, or I can use it in a calculation, or I could check, put a conditional statement. If D is less than this, stop, which you saw that was one of the drive commands. So we can have Rover reading values and then acting upon them once it's read them. And there's a range of sensors you can plug in because they've got the Innovator in there, and it's got 3 input and 3 output ports still available for users to have whilst driving Rover around. What about senior maths? So we've seen some stuff that we can do for junior maths. So at the start of this webinar, I talked about a self-parking option. So this one's already up on the TI Australia website. It's the idea that students have got to self-park Rover, or in the first stage at least, they're exiting a parking spot. And the reason why I did this is because of the mathematics that the students are going to use. And like all good tech explorations, I guess, there's some simulations involved as well. Before they're allowed to get the vehicle out on the road, they need to test it in the simulator, because in the real world, you don't go and build this object before you test it. Pretty much everything now is done with a simulator as well. So you can see some of the objectives in there. We've got transformations of trigonometric functions, polynomials, derivatives of polynomials, antiderivatives of polynomials, simultaneous equations, distance between a point and a function as a challenge, and also defining hybrid functions or piecewise functions. And there's a list of vocabulary that students have to work with. And let's have a look at the actual activity itself. So it says, suppose the curve, there's some precursor stuff up the top, but suppose the curve is modeled by the function. So we can see that this vehicle is located at the origin, and you can see the red line, the dotted line, and it's going to reach the point P. So point P is where we want the vehicle to stop. Now, there's a few things that students have to consider. That comes about once they've actually taken the simulator through. So what does the TI-Nspire file look like? Let's have a look at driver-assisted parking. I've put in a trigonometric function that should do the job. And then I'll navigate on to page 1.2 where we have our simulator. And you can see there's a little blue Rover. Now, I haven't drawn Rover exactly to scale, but it's close. There's a show hide option here. Let me just turn that off for the moment. And the students can drag Rover along to make sure it can get out of the parking spot just nicely. So the idea is that Rover starts parallel to the curb being parallel to the x-axis. Mathematically, we'd say it's got a turning point there. And then Rover proceeds and wants to end up parallel, not too far, parallel to the vehicle which it's passing. Now, that wouldn't matter whether it was a parked car or just a lane change, although a lane change would be thinking about velocity and time embedded in that problem. The next part of the question on the activity says, so initially this point P here was at 30, 10. What if we changed it to 30 but only 8? So in other words, it's going to finish its drive a little bit closer to vehicle B. And the students just change their equation here. That one's a no-brainer. I'll do that one. So we can see now the curve's a little bit tighter. Do we really need to drive out as far as what we did? Perhaps we'd even moved into the other lane. But let's have a look. Looks pretty good. Rover got past, but, oh dear, we might be scraping the paintwork there. And one of the questions it poses is, so how close does it get to vehicle B? Or in other words, in this particular example, what's the maximum width we can have for Rover? So what we're now doing, the students are given the coordinates of the point on the green car, car B, and it says, well, what is the closest point on that car to our curve? So the distance between a point and the curve. And it's kind of nice at the edge of Rover is kind of hinting at the students that you could look at tangents to the curve, and that tangent would be at right angles to the line connecting that point and this point here. So when we get to the point that Rover is closest to the car, like there, we can see that line connecting the green car to Rover's pivot point, if you like, is approximately at right angles to the side of Rover, which also means, of course, it's tangent to the curve. So in this particular case, 3.6 units, whatever those units might be, we're just talking about coordinates on the x-axis. I guess theoretically the students can come up with the entire distance equation and graph the distance equation to see how that changes with time. But remembering that that distance it's measuring is just from some center point on Rover. In the case of Rover, that's halfway between its two front wheels is where it tends to drive from. So there's a simple one, but that's not the only curve or path that Rover might follow. So if I go back to the question sheet and scroll down, so the students determine the values for A, B, H, and K, and they run through the simulator. And once they're done, we change the value of P, and it says that Q, that is the point on the green car, has those coordinates. What's the closest distance? Define a function d of x and find that distance. Question 2 says, what if we did it as a polynomial? In other words, instead of using a trigonometric function, let's do it with a polynomial. And of course, there's a reason why we're going to use a cubic function, because this function here will have potentially two turning points. So what information do the students have to start with? Well, of course, if we're thinking about the actual curve itself, they know that one of those turning points is at the origin because Rover is parallel to the curve at that point. And then when it reaches point P, somewhere over here, which the students are given the coordinate at that point, it's again parallel to the curve. In other words, we have another turning point. So the students have two turning points, and therefore they know something about the derivative function, so they can define the gradient function, let's call it g of x or f dashed of x, and they know the coordinates of two of the turning points, so they can get a general equation for those two zeros of that derivative function. When they anti-differentiate it, they can work out the constant. The graph passes through C, so the constant disappears. They end up building a function, a cubic function. Now, because I figured I'd probably run out of time, I decided I'd cheat and I'd load up the answers as well. So we've got the self-parking car, and then if I tab over one more, I've got the answers. So we are generous, we put the teacher answers up there as well. You'll see, like, say, for example, in that previous question, the distance formula, it's just been left as x minus 24 squared plus, and it's got the other function in there, f of x all squared, etc. We'll scroll down a little bit. And here's a function that seems to work, a cubic function, x squared by 45 minus x all over 1,350. That's based on a specific coordinate of P that we're trying to avoid. So if I go back here and I'll put that cubic function in, it'll be a challenge doing that with one hand and holding the phone with the other. Let's see how we go. We've got, and I'll use my fraction key, x squared times, better put a multiplication sign in there just in case, and we had 45 minus x. That's all over 1,350. You can see the numbers are not necessarily delightful, but they're real life situations. So there's our new curve. It looks slightly different than the trigonometric function, and Rover manages to miss the car quite well. So does it miss by a greater or lesser amount than the trigonometric function? Well, let's just check it and see exactly how similar are those two curves. I think we had 5 times sine, I'm going to say it was pi over 30 times x minus 15, see how good my memory is, plus 5. They do look remarkably similar, don't they? Let's just change the colour of the graph. And look at how similar the trigonometric function and the cubic function are. So we really are almost doing the same curve. In fact, when the students check to see what is the difference between that cubic function and that trigonometric function, it's like 0.1 difference. That's all there is. And if you want to lead off into different branches of mathematics, we can talk about how polynomial functions can model trigonometric functions. It's the whole idea of the Taylor series polynomials for your trigonometric functions being things like x minus x cubed on 3 factorial plus x to the 5 on 5 factorial, etc. Those sorts of things. So there's that aspect to it as well. So we can branch off and have a look at a whole lot of other parts of mathematics if you want to use it as a segue into those areas. So there you can see, remarkably similar. And as it shows you there, the greatest difference between the two is 0.1, and that occurs when x is about the halfway point or 0.8 or something. Oh, sorry, 8 point something. Then the students take Rover for a test drive. It's time to get Rover out on the track. Now, for the first one, we tell them that they can measure up some point P. They decide where that's going to be, and then they'll put those values in. So they come up with a general equation, as you can see there, in terms of, and it looks very similar to what we had before. So we want to find out, if we have the general coordinates of point P, what would the general equation look like? So students can enter that, and then the calculator will prompt them before Rover takes off, what are the coordinates of the point you are trying to get to? And if they've got their equation wrong, Rover's going to crash. And there's a little warning sign that says, for this investigation, we are not using the ultrasonic sensor, so make sure that you're ready to stop Rover in the case of an impending collision. But some of the cool programming they've done with that is that if Rover detects that it's not moving and it's trying to, it eventually turns itself off, doesn't it, Jody?
At the most awkward of times, usually.
Yeah, good point, good point. And in the last section, because we're almost out of time here, in the last section that students do in this activity, there's another parameter is added to the problem, and that is, let me just scroll down a bit further so people can see it. There it is there. There's a picture of Rover, and you can see the graph that Rover's drawn to get out. So I put Rover's box in front of it, and I put the grid on just so that you could see that it's essentially just drawing a curve. It gives you some sort of a scale on how things are, and Rover managed to get out of the parking lot unscathed. And in this last section, Rover becomes completely autonomous. That is, we switch on Rover's sensor, and here's where it gets a lot more challenging for the students. So we tell them that Rover will be placed at the origin, and the box that Rover's going to drive around, the other vehicle, will be set some distance away, determined by the teacher. And the student's equation needs to get Rover out of that parking spot without hitting the box. So here's where it gets messy, because we cannot think of Rover as a point so much anymore. They need to consider, how much clearance do I want to give Rover in my equation? What point do I want to head it towards at point P? But also, I don't know what that distance D is. But what happens is the program is set up automatically so it will measure this distance D using Rover sensors at the front, its ultrasonic sensor, and once it's measured it, it stores it in D. So the equation that the students come up with needs to have the coordinates of the point where it's going to head towards and this value D. Everything is going to be in terms of D and, of course, X. And then we run the program. So the kids only get to define their function, that's all. And when the program runs, there is no intervention by the student. The box is placed in whatever spot the teacher decides to place it in. And there's some advice, if teachers are using this activity, there's some advice for teachers about how close you can get it, because we know if it's too close, Rover will not physically be able to get out of there. So there's a nice little activity for students to do. The distance is returned to D. It's a parameter. We're translating this function by some distance D, and the kids come up with a general equation to go through some point P, which is also dependent on D. and testing it, Rover comes out of it quite nicely, providing the students give Rover enough of a gap. And there's the general equation just about to come up on your screen. This is our advanced driver. You can see we have, it looks a little bit like it did before. I can now see there's one bracket or parentheses missing off that expression. It should be closing that bracket off. And that's a general equation the kids come up with. And if they do that, so in other words, here's the original one that we had, and then the general form, and that's where this extra bracket needs to go in just here on our answers, that will work. And it says that the box should really be placed about 15 centimetres in. Otherwise, it's a bit hard because by the time Rover turns, its back end will still potentially hit and collide with the box. And then, of course, the last part, which is an extension task, is improving the model. So both the trigonometric and cubic functions are what we call rotationally symmetrical. That is, the exit curve and entry curve, entry being entering onto the main road. As it exits the parking spot and enters the main road, that curvature is the same. It's rotationally symmetrical. Both functions rotationally symmetrical about that point of inflection. So this time what the students do is they define a quadratic function for g of x and a quadratic function for h of x, both having turning points at the origin, well, g of x having a turning point at the origin, excuse me, and h of x having a turning point at point P. And now they can control the curvature at the start and the end, so we no longer have that same curve. So the students come up, they do some simultaneous equations, and if I just scroll back a bit there, the curves have to join smoothly, and this is where a lot of our calculus comes in, the knowledge that those two curves have to join smoothly at whatever the point is, point Q, in the middle. So they need to know what is the gradient of g of x and what is the gradient of h of x. And I need to make sure that those gradients are the same at q of x. If there's teachers in Victoria watching, they may remember a cycling along the Yarra, which was done back in the 90s, I'm going to say, as a BCE SAC. Very sort of similar idea where we're joining curves smoothly. And that's about the end of that activity. And
wonderful.
It's about the end of our webinar as well. So that activity can be downloaded from the Texas Instruments website to demonstrate. Where are we? Oops, jumped out too far. If you go onto the TI Australia website and go onto Senior Curriculum, Inspirations, it's in the relevant spots for most of the states. I'll do it for Victoria. The sort of content that we're talking about is applicable to mathematical methods, Year 12, and there's our self-parking rover and all the attachments, including the TI-Nspire file that we're using it, TI-Nspire activity, the student activity, and most importantly, the teacher answers.
Cool. And before we finish up, Pete, I just wanted to mention we will also be sending out a link to just a basic beginner's guide to driving the Rover. I've used it with my Year 7 students, parents, and some younger kids, and they have the quite step-by-step, here's how to get the Rover at its base level, moving, turning, and having those conversations about really simple programming so they can build them up as they go along with this wider skill set so they can be parking and the like. So this is to help them walk and crawl before they start driving around.
And which is fantastic that they've actually got that getting started idea, because I would not have thought of doing the graphs. I think the graphs is a brilliant one. And just as we're closing up, check out our YouTube channel. As Jody mentioned, he has a lot of videos up himself as well, so maybe track down Jody's YouTube channel. Maybe you should put a link in the documents that you've got there, Jody, to your YouTube channel. And if you haven't already, subscribe to our e-newsletter so you can keep in touch with us and find out about all the events that we're running. And if you have any questions about our products, there's some phone numbers for you if you're in Australia and also in New Zealand. And that about draws us to a close. So thank you for coming, and we'll finish up there. And thank you, Jody, for your presentations and contributions too.
You're welcome. I really enjoyed being part. The rover is really exciting, getting maths moving, and part of putting that M back into STEM.
That's it. All right. Thanks, everyone, for joining. And hopefully we'll catch you at our next webinar, which I believe is next week. Bye for now.